Welcome! Today, we'll tackle an exciting problem from LeetCode, problem number 652, find duplicate subtrees. This problem challenges us to identify and handle duplicate subtrees in a binary tree, a concept that blends tree traversal and hashing techniques. We'll explore an intuitive brute force approach and move towards an optimized solution. Let's dive in. In this problem, you are tasked with identifying duplicate subtrees within a binary tree. Let's start by understanding what a subtree is. A subtree is formed by taking any node in the binary tree and including all of its descendant nodes. Now, duplicate subtrees are subtrees that have the exact same structure and node values, even if they originate from different parts of the tree. The goal is to find all such duplicate subtrees in the tree and return their root nodes. For example, if two nodes in the tree both have identical subtrees underneath them, those subtrees would be considered duplicates. The input to the problem is the root node of the binary tree, and the output is a list of tree node objects. Each object represents the root of a duplicate subtree, and the order of the results doesn't matter. Let's look at the first example to make this clearer. The input binary tree has the structure shown, where the root node is 1. The left subtree of the root is a tree with the root value 2, and that subtree itself has a left child with value 4. On the right side of the root, there is a tree with the root value 3. This subtree has two children, a left subtree with root value 2 and a right subtree with root value 4. Now, notice that the subtree rooted at 4 appears multiple times in the tree, once as an individual node under the left subtree of 2 and once under the right subtree of 3. Additionally, the subtree rooted at 2, which includes a left child with value 4, is also duplicated. The output for this example is a list containing the root nodes of these duplicate subtrees, one for the subtree rooted at 4 and another for the subtree rooted at 2 with its left child. In the second example, the binary tree is smaller. The root node has a value of 2, with two child nodes, each having the value 1. Here, the duplicate subtree is simply the single node subtree with root value 1, as it appears twice in the tree. So, the output consists of a single tree node object representing the root of this duplicate subtree. This example highlights that even the smallest subtrees, such as those with just one node, can be identified as duplicates if they appear multiple times. Finally, in the third example, the binary tree consists of only one node with the value 0. In this case, there are no duplicate subtrees because a single node does not repeat within the tree. Therefore, the output is an empty list. The problem also includes some constraints and edge cases to consider. For instance, the tree can have up to 5,000 nodes, so your solution needs to handle large inputs efficiently. Node values range from -200 to 200, and each node in the tree is a distinct object. Some edge cases to think about include trees with only one node, trees with entirely unique values, and trees with multiple overlapping duplicate subtrees. Keeping these constraints in mind will help in crafting a robust and efficient solution. To solve the problem of finding duplicate subtrees, we first considered the brute force approach. The intuition behind this method is straightforward. For every node in the tree, we extract its subtree and compare it with every other subtree we've seen so far. If two subtrees match, we mark them as duplicates. However, this approach involves traversing the entire tree multiple times, which makes it computationally expensive. Specifically, the time complexity can go up to n squared, in the worst case because we compare n subtrees, and each comparison itself takes n time. Additionally, the space requirement is n to store the extracted subtrees. While this method is simple to implement, it becomes highly inefficient for larger trees due to the repetitive comparisons that add significant overhead. To improve upon the brute force approach, we use an optimized strategy based on serialization and hashing. The key idea here is to represent each subtree as a unique string. This allows us to efficiently compare subtrees by comparing their serialized forms instead of their actual structures. Using a hash map, we can track the frequency of each serialized subtree, and any subtree that appears more than once is identified as a duplicate. To implement this, we perform a post-order traversal of the tree, where for each node, we generate a serialized string of the form left_subtree_serialization, node_value, right_subtree_serialization. This string captures the structure and values of the subtree rooted at that node. We then store this string in a hash map, updating its frequency. If any serialized string's frequency reaches 2, we add the corresponding node to the result list to avoid counting the same duplicate multiple times. This approach is efficient because serialization transforms subtree comparisons into simple string comparisons, and the hash map ensures constant time lookups for frequency tracking. The optimized approach using serialization and hashing has significant advantages in terms of complexity. The time complexity is O(n), because we visit each node exactly once during the post-order traversal, and generating the serialized string for each node is linear in time. The space complexity is also O(n), which accounts for the hash map storing serialized subtrees and the result list of duplicate nodes. While this method is efficient and scalable, especially for large trees, it does require additional memory for the serialized strings and the hash map. As an alternative, we can use tree canonicalization to reduce memory usage. Instead of strings, this method assigns a unique integer ID to each distinct subtree structure. The IDs are then used to track subtree frequencies in the hash map. While this approach is more memory efficient than string serialization, it involves additional implementation complexity, such as managing unique ID assignments during the traversal. Tree canonicalization offers a similar time complexity of O(n), as each node is still visited once during the traversal. The space complexity remains O(n) for the hash map and result list, but canonicalization reduces memory usage by replacing serialized strings with compact integer representations. However, this comes at the cost of slightly more complex implementation details, such as the need to assign unique IDs to subtree structures dynamically. Additionally, this approach may feel less intuitive compared to serialization, which directly captures the subtree structure and values as a string. While canonicalization is efficient, its added complexity may not always justify the marginal improvement in memory usage, especially for problem constraints that allow for a more straightforward solution. Ultimately, the chosen strategy is the optimized approach using serialization and hashing. This method strikes a balance between simplicity and efficiency, making it well suited for solving this problem. By leveraging post-order traversal and hash maps, we avoid redundant subtree comparisons, significantly improving performance over the brute force approach. Serialization allows us to reduce subtree comparison to string comparison, which is both intuitive and effective. While tree canonicalization offers greater memory efficiency, the increased complexity of implementation makes it less appealing in this context. The insight that subtree comparison can be replaced by string comparison via serialization is the key to this solution's scalability. With a time complexity of O(n), this approach is robust and handles large binary trees gracefully, meeting both the problem's requirements and practical considerations for real-world applications. To tackle the problem of finding duplicate subtrees, we can start with a brute force approach. The idea is to compare every subtree with every other subtree in the binary tree. First, we traverse the entire tree, beginning at the root node. A depth-first traversal, or DFS, is used to ensure that each node and its corresponding subtree are visited systematically. Once we arrive at a node, we create a unique string representation of the subtree rooted at that node. This involves serializing the subtree's structure and values into a format that captures both the node relationships and their data. A common way to serialize is by using a pre-order traversal, which processes the current node first, then the left child, and finally the right child. Placeholders are included for null children to prevent structural ambiguities. For example, if a subtree is rooted at node A with left child B and right child C, its serialization might look like A, B, C. This unique representation is the foundation for comparing subtrees in this approach. After generating the serialized representation for each subtree, we need to store these representations. A list or set can be used for this purpose. As each subtree is serialized, we check if its string representation already exists in the collection. If it doesn't, we simply add it. However, if it is found, this means the subtree is a duplicate, and we mark it accordingly. To identify duplicates, we compare each serialized subtree with all previously stored serializations. This comparison is a straightforward string comparison. Once a duplicate subtree is detected, we store its root node in a separate collection, such as a list or set, dedicated to duplicate subtrees. Finally, after completing the traversal, we return this collection of duplicate subtree root nodes as the result. The key to this approach lies in the serialization of subtrees. By converting the subtree structure and values into a unique string representation, we simplify the problem of subtree comparison into a string matching task. However, this brute force approach has its limitations. Since every subtree is compared with every other subtree, the time complexity is roughly n squared for a tree with n nodes. This makes the method inefficient for large trees. Using a simple list for storing serialized subtrees contributes to the inefficiency, as each lookup requires a linear search. While this approach is conceptually straightforward, it becomes computationally expensive as the size of the tree grows. The choice of data structures plays a significant role in the efficiency of this algorithm. A list can be used to store all serialized subtrees, allowing sequential comparisons. However, the drawback is that linear searches make this approach slower for larger trees. On the other hand, a set can be used to store the root nodes of duplicate subtrees. The advantage of using a set is that it inherently avoids duplicate entries, ensuring that each duplicate subtree root is stored only once. While these data structures work, they leave room for improvement in terms of performance, especially when dealing with larger datasets. To optimize the algorithm, we can replace the list with a hash map. Instead of sequentially storing serialized subtrees, we use the hash map to store each serialization as a key and its occurrence count as the value. This allows duplicate detection in constant time, reducing the complexity significantly. Another optimization is to cache the serialization of subtrees. By avoiding redundant computations, we save time during comparisons. Depth-first traversal remains the traversal strategy, but by serializing subtrees starting from the leaves and working upwards, we ensure efficient memory usage and computation. These optimizations collectively improve the algorithm's average complexity from n squared to n, making it much more scalable for large binary trees. To solve the problem of finding duplicate subtrees, we start by importing the necessary library, defaultdict, which will help us efficiently count occurrences of subtree serializations. Inside the solution class, we define the main function findDuplicateSubtrees, which takes the root of the binary tree as input. Within this function, we have a helper function called serialize. This function is responsible for converting each subtree into a unique string representation. Now, if the current node is null, we simply return the string hashtag, which acts as a marker for null nodes. Otherwise, we recursively serialize the left and right subtrees. Once both are serialized, we create a unique representation of the current subtree by combining the value of the node with its left and right subtree serializations, separated by commas. This unique string acts as the key for identifying duplicate subtrees. We then update the count of the serialized subtree in a dictionary called subtree_count. If the count of a subtree reaches exactly 2, it indicates a duplicate, so we add the root of this subtree to the duplicates list. Finally, the function returns this serialized string to be used by its parent node. After defining the serialize function, we initialize two key data structures, subtree_count, a dictionary to track the occurrences of each serialized subtree, and duplicates, a list to store the roots of duplicate subtrees. The process begins by calling the serialize function on the root of the tree, which recursively traverses the entire binary tree, serializing each subtree and detecting duplicates along the way. Once the traversal is complete, the duplicates list contains all the duplicate subtrees, and we return this list as the final result. This approach ensures an efficient and systematic way to detect duplicate subtrees while leveraging the power of serialization and hashing. Here, we begin by defining the findDuplicateSubtrees method, which takes the root of the binary tree as input. The goal of this method is to identify all duplicate subtrees in the tree. To do this, we use a hash map called subtreeCount to keep track of how often each serialized subtree appears, and a list called duplicates to store the roots of duplicate subtrees. The main work is delegated to a helper method called serialize, which recursively traverses the tree. In the serialize method, we first handle the base case where the current node is null. For null nodes, we return a placeholder string, in this case, hashtag. Next, we recursively serialize the left and right subtrees, storing the results in left serial and right serial. Then, we construct a unique string representation of the current subtree by combining the value of the current node with its left and right serializations, separated by commas. This string serves as the key for our subtree count map. If this key has been encountered before, we increment its count, otherwise, we initialize it to 1. If the count reaches exactly 2, we add the current node to the duplicates list, ensuring that each duplicate subtree is only added once. Finally, the serialized key for the current subtree is returned, allowing the recursion to continue building the full tree's representation. The implementation concludes with the definition of the treeNode class, which represents individual nodes in the binary tree. This class includes an integer val for the node's value, and references to the left and right child nodes. Several constructors are provided: a default constructor, a constructor that initializes the node with a value, and one that initializes the node with a value as well as its left and right children. This class is provided by LeetCode, so you won't need to define it yourself during practice. Together, the tree node structure and the methods we've implemented allow us to systematically traverse the tree, serialize its structure, and identify duplicate subtrees efficiently. To solve this problem, we need to identify duplicate subtrees in a binary tree. Let's start with a simple example. Here's the input tree, where node 1 is the root. The left subtree of node 1 has node 2, which itself has a left child, node 4. The right subtree of node 1 has node 3, which contains 2 children, another node 2 on the left and node 4 on the right. The left child of this second node 2 is also node 4. First, we initialize 2 data structures, subtree_count, a dictionary to keep track of how often each subtree serialization appears, and duplicates, a list to store the roots of duplicate subtrees. Then, we begin serializing the tree starting from the root. The left subtree of node 1, starting at node 2, is processed. For node 2's left child, node 4, there are no children, so it serializes as 4 ###. Next, node 2 is serialized as 2 for ###, since its left child is node 4 and it has no right child. Moving to the right subtree of node 1, we process node 3. Its left child, node 2, is serialized similarly to the earlier node 2. Starting with its left child, node 4, we get for ###, and for node 2 itself, we serialize it as 2 for ###. The right child of node 3, node 4, serializes as for ###. Combining these, node 3 is serialized as 3 for ###. Finally, the root node 1 is serialized as 1 for ###, 3 for ###. As we update the subtree counts, we notice that for ### appears 3 times, so we add the first occurrence of node 4 to the duplicates list. Similarly, 2 for ### appears twice, so node 2 is added. The subtree for node 3 only occurs once, so it is not duplicated. The final output for this example is duplicate subtrees rooted at nodes 4 and 2. Now let's consider a simpler case, a single node tree. Here, the tree contains only the root node, which is node 1. We start by initializing subtree_count as an empty dictionary and duplicates as an empty list. The serialization process begins with the root. Since node 1 has no children, its left and right serializations are both hashtag. Combining these, node 1 is serialized as 1 ###. When we update the subtree counts, we see that 1 ### occurs only once, so there are no duplicate subtrees in this case. The final output is an empty list, indicating no duplicates were found. Finally, let's examine a tree with identical subtrees. The root node is 1, with 2 child nodes, both labeled 2. Each of these nodes has a left child labeled 3. Starting with the initialization, we set subtree_count to an empty dictionary and duplicates to an empty list. The serialization begins with the left subtree of node 1. Node 3 is serialized as 3 ### since it has no children. Then, its parent, node 2, is serialized as 23 ###. Moving to the right subtree of node 1, we follow the same process. Node 3 is serialized as 3 ###, and its parent, the second node 2, is serialized as 23 ###. Finally, the root node 1 is serialized as 123 ###, 23 ###. When updating the subtree counts, we observe that 3 ### appears twice, so node 3 is added to the duplicates list. Similarly, 23 ### also appears twice, so node 2 is added. The final output for this example is duplicate subtrees rooted at nodes 3 and 2. To analyze the time complexity of our solution, we start with the process of serializing the tree. Serialization involves visiting every node in the tree exactly once, which means that for a tree with n nodes, this step takes n time. However, during serialization, we also concatenate the serialized strings of the left and right subtrees to form the key for the current subtree. This concatenation operation depends on the length of the serialized subtree, which we denote as k. Hence, the time for serialization includes an additional k per node. We'll explore the value of k shortly. Next, we store these subtree keys in a dictionary and update their counts. Dictionary operations like insertion or lookup are on average 1, and since we process n nodes, this contributes an overall n to the time complexity. These two main steps, serialization and dictionary updates, form the basis of our time complexity analysis. Now, let's examine the impact of the key lengths on the time complexity. The length of the serialized key depends on the size of the subtree. In the worst-case scenario, such as a highly unbalanced tree that resembles a linked list, the size of the serialized key for a node can be proportional to n. On the other hand, in a balanced binary tree, the average size of a key is much smaller, around log n. Therefore, the worst-case time complexity arises when we need to concatenate long keys in an unbalanced tree, leading to n squared. However, in a balanced tree, the average case time complexity is reduced to n * log n. Shifting to space complexity, the recursion depth of the serialize function directly impacts the call stack usage. For a highly unbalanced tree, the recursion depth reaches n, while for a balanced tree, it is limited to log n. In addition to the call stack usage, space complexity is also influenced by the storage requirements of the dictionary that keeps track of serialized keys and their counts. In the worst case, where all subtrees are distinct, there could be n unique keys stored in the dictionary. The space required for these keys depends on their length. For an unbalanced tree, the total space for keys can reach n squared, while for a balanced tree, it is n * log n. Another component of space complexity is the list of duplicate subtrees. This list stores pointers to the roots of duplicate subtrees. Even in the worst case, there can be at most n duplicate subtrees, and since each entry in the list is just a pointer, the space required is n. Combining these factors, the worst-case space complexity is n squared for an unbalanced tree, while the average-case space complexity is n * log n for a balanced tree. Finally, comparing this solution to a naive approach, which requires n cubed time, the optimized method is far more efficient. By leveraging serialization and a dictionary, we avoid redundant subtree comparisons. To summarize, the time complexity of the optimized solution is n squared, in the worst case in n * log n, on average. Similarly, the space complexity is n squared, in the worst case in n * log n, on average. This represents a significant improvement over the brute force approach, which would require n cubed time due to the inefficiency of comparing every pair of subtrees. By using serialization and a dictionary, we achieve a much more scalable and efficient solution for detecting duplicate subtrees. One of the most common mistakes when solving this problem is incorrectly serializing subtrees. It's essential to explicitly include null nodes in your serialization, as omitting them can lead to incorrect comparisons. For instance, the structures 1, null, 2 and 1, 2, null are distinct, but skipping null nodes might treat them as identical. Another frequent error is relying on an inefficient brute force approach, where the tree is traversed multiple times for each comparison. This can lead to a time complexity of n cubed, which is impractical for larger inputs. Additionally, failing to consider edge cases like single-node trees, entirely identical subtrees, or deeply nested structures can result in missed duplicates or incorrect outputs. If you're using a hash map to store serialized subtrees, be aware of potential hash collisions. Subtrees that appear to match based on their hash values should be explicitly verified for equality. Lastly, be mindful of memory usage. For larger trees, storing full serialized representations can consume significant memory, so look for ways to optimize your solution using more concise data structures. This problem is an excellent test of your ability to apply recursive thinking and recognize reusable subproblems. By breaking the tree into smaller subtrees, you can focus on efficiently identifying duplicates. When evaluating approaches, be aware of their trade-offs. While brute force might seem intuitive, it's computationally expensive. Hash-based solutions, where serialized subtrees are stored in a hash map, strike a balance between time and space complexity. For those aiming for an advanced approach, techniques like custom hashing or optimized traversal methods can further refine your solution. Ultimately, the goal is to achieve O(n) time complexity. This is possible with a post-order traversal, where subtrees are hashed as they are visited, ensuring that each node is processed only once. Strive for this level of efficiency to make your solution robust and scalable. This problem ties into several related challenges that can help deepen your understanding of binary tree operations. The canonical problem, LeetCode 652, focuses specifically on finding duplicate subtrees. Another related problem is LeetCode 863, which involves identifying all nodes at a specific distance k within a binary tree. This problem hones your tree traversal and recursive problem-solving skills. LeetCode 105, which centers on constructing a binary tree from pre-order and inorder traversals, is particularly helpful for understanding tree construction and serialization concepts. Lastly, LeetCode 222, which involves counting complete tree nodes, provides insight into efficient traversal techniques under constraints. Exploring these problems will strengthen your ability to approach tree-related challenges from a variety of angles. There are several alternative approaches to solving this problem, each with its own advantages and trade-offs. The first is hash-based serialization, where you serialize each subtree during a post-order traversal, store the serialized strings in a hash map, and count their occurrences to identify duplicates. While this method is efficient in time, with O(n) complexity, it may consume significant memory for larger trees due to the storage of full serialized strings. Another approach is tree canonization. Instead of serializing subtrees, you assign unique IDs to structurally identical subtrees and map these IDs in a hash map. This method reduces memory usage compared to serialization but can be more challenging to implement. Finally, you can use a custom hash function. During post-order traversal, compute a unique hash for each subtree instead of storing the entire serialized structure. This not only reduces memory usage but also avoids the overhead of storing long strings. However, designing the hash function carefully is critical to prevent hash collisions, which could compromise the solution's accuracy. Each approach provides unique benefits, and the choice depends on the constraints and requirements of the problem at hand. Great job! Today, we covered how to find duplicate subtrees using serialization and hashing for efficient comparison. You've learned how to optimize tree traversal and apply these concepts to real-world hierarchical data. If you enjoyed this, please like, share, and subscribe for more coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!